All right, so welcome everybody to Hoon Academy Lesson 4. So this lesson's going to be a bit of a break from the last few lessons. I know things were starting to get a little more complex with that lesson 3. This one's going to be a shorter and easier topic. And we'll also be having a real break after this class. So for the next 2 Saturdays, there's not going to be any class due to the holidays, and the next one will be on January 6th. For office hours, I will hold an office hours this Monday at 5 p.m. Eastern time. But office hours will be also on break until Friday, January 5th. So that's the Friday before the Saturday where class picks up. That being said, I'm going to be online and checking my messages throughout this time. So if you have any homework questions or any general questions, definitely reach out to me. I will help you as best I can, as fast as I can. Since we have about 3 weeks off, it's a great chance to catch up and get up to speed on these first 5 lessons. And this officially marks the halfway point of the course. So congratulations on making it here. All right, so let's get into our first big topic for today, which is lists. All right, so recall from last lesson that we made cell types with the buckhole room, and those expect a certain fixed number of children. It's like they create a fixed structure, right? For example, if I use this code, pin that in the chat in case you want to follow along. So I'm using this Dojo syntax to pin this structure to my Dojo state under the face 2 nums. So, and this buckhole is creating a cell type, right? It's saying, let me create a structure which has a pat UD in the first cell, in the first slot, and a pat UD in the second slot. I close it with this tis. So press enter. If I try to cast this cell of 3 numbers to this 2 number structure I just made, it's going to fail, right? That seems pretty predictable based on what we learned. And I can also call it as, if I call it as a gate, it's also not going to work because there's just a structure mismatch there, right? So, and likewise, if I make a structure that's 3 numbers, and I try to cast a cell of 2 numbers to it, that's also not going to work, right? Because there's just a type mismatch there. I try to cast a cell of 1, 2 to this 3 number structure that I just created, and I get an error. So this is a bit restrictive. Sometimes you need a data type that doesn't know in advance how many entries it's going to have. And in Hoon, certain molds are what we call recursive molds, where instead of requiring a fixed size, they specify a flexible structure that can be as small or as large as you need. So the simplest example of this, and what we're going to learn today, is the list. So a list is a structure with the same data type in all entries and a variable length. So 3 people were waiting. All right. So for the 3 people that just joined, I just said we're covering lists. A list is a structure with the same data type in all entries and a variable length. Let's try a simple example of making a list of numbers with this code right here that I'm going to put in the chat. Okay, so what is going on here? Let's break it down. Let's dissect it bit by bit. First, let's look at this latter half of the code right here. Recall that every data structure in Urbit is a binary tree. The internal data representation of this is a cell of 6 things. So the internal data representation actually looks like this, right? Because you'll recall the cell structure looks like this. And if you recall from the lesson 1 exercises where you converted between these things, this cell structure looks like this tree right here. So we have a rightwards branching tree whose last element is this null character sig. We call this a null terminated tuple. So it's a tuple that ends in a null. This is the necessary structure for something to be interpreted as a list. And the cell structure looks like this, just as we said. And the sugar syntax just gets rid of these extra brackets and makes it look clean like this. But this is this underneath. The null terminated tuple is a privileged structure in Hoon. So there's a few different syntax options. You actually see here what the output of this expression, it has the sig in front. And actually that's just the sugar syntax too. This is exactly the same as this. For legibility reasons, when the sig is in front, it makes it easier to see up front. Oh, okay, like I read the first character, I know this is a null terminated tuple. So that's just a bit of convenience syntax. There's also a rune that you can use to construct a null terminated tuple. So col sig, right? We've been working with col runes so far. They create cells, right? Col sig is very, very similar. It takes an unlimited number of children and you close it with this tis. And it just puts all those children into a null terminated tuple. So it just puts them all in a cell and adds the sig at the end. So like if I do col sig 1, 2, 3, I'm gonna get this, right? So if we went back to the structure and we instead replace this sig at the end with this number 6 or any other number or structure, this can't be a list anymore. This is just a tuple of 6 things. For something to be a list, you need that sig at the end to denote its structure. Just sig by itself is also a null terminated tuple. It's the smallest one because a tuple containing one thing is just equivalent to the thing itself. So this is the smallest possible null terminated tuple. However, like we know that this character serves many purposes. It's number 0 underneath, right? When the Hoon parser sees this character, it's not going to automatically interpret that to be a list. If you have a cell like 1, 2, sig, the Hoon compiler doesn't assume that to be a list. Because we're using the same syntax for tuples and lists, it's dangerous for the compiler to assume this is a list. Like for some reason you might have a data structure where you want to have 3 sigs in a cell, and maybe that you actually want it to be a 3 tuple, not a infinitely expanding or contracting list. So the parser doesn't assume that structures like these are lists, but they can be lists. And that goes back to our piece of code here. So what's this first half of this piece of code doing? It is saying, let me take this structure and let me make sure we know that we're parsing it as a list. Okay. So let's notice this senhep rune right here. So what is that doing? People recall what this senhep rune means? Yes, that's correct. So Dan says senhep is for calling a gate. So in particular, if we're using senhep here, yes. So if we're using senhep here, senhep's first argument is always a gate. So that means this term list is actually a gate. So in particular, this term list is what we call a mold maker gate. So list is a gate that takes a type and returns a type. It takes a type, which is it takes any possible type as an input, and it returns a type, which is a list of that type. So here we're passing the list pat_ud as the argument to the gate list, and that returns a type, which is a list of pat_ud numbers. And in production Hoon code, you'll most often see this in this following sugar syntax with the brackets, because it's nice to read like that, right? These brackets kind of say, oh, this is a list of pat_ud. But you should always know that this desugars to the gate call underneath. And finally, the last part of this code, we're just saying, let me cast this value, this cell of 6 things that ends in a sig, to this mold, which is list of pat_ud. So that's the entire breakdown of this piece of code. Are there any questions on that? All right. So we can use the mold maker gate list with any types. So I mentioned this before. So for example, in last lesson, we made this type union of reptile, right? So the syntax says we're pinning to the dojo state. We're storing this in the dojo. A type union, buckwhat, that is either going to be a send snake, a send lizard, or a send crocodile. And now let's make a list of those things. So here we're saying, I have a cell with send crocodile, send snake, send lizard, and sig. That's a list of 3 things. I mean, we can even add a lizard to it. It's not exclusive, right? So, and we're saying, let me make a type, which is a list of this reptile type that I just created and stored. This creates a new structure, a list of this reptile type, and then we're going to cast this structure to that. Let me fix the spacing. There we go. So that passed the type check. And the sugar syntax would look like this: ket_hep list reptile listing. We can also make lists of other lists. So let's check out this code right here. So here we have a null terminated tuple with 3 entries. Each of its entries is also a null terminated tuple of A, B, C, sig, D, E, F, sig, X, Y, Z, sig. So it's a tuple with 3 tuples as its entries. Here we're calling list on pat_t as a gate, and then we're calling list on that list structure that we created. So there's 2 send_hep gate calls here. And we're saying that this structure, we want to interpret this as a list of lists of pat_t text. And there we go. So this is much easier to read in the sugar syntax. Here's the same data structure. And here we're saying call list on pat_t that gives you a mold, which is a list of pat_ts. Call list on that, and that gives you a list of lists of pat_ts. All right. Any questions on that? All right. So list is the first mold maker gate we're going to learn, but there are many others we're going to learn later. There's a lot of familiar data structures if you're coming from other programming languages, such as set. Set creates a set of any type. A set is kind of like a list, but everything has to be unique, and it's unordered. A map, so that's like key value pairs, like a dictionary, right? You could go into a dictionary, there's a word, there's a definition under it. You can create a map from any type to any other type. All right. So, question for you guys. If a list is represented underneath as a binary tree like this, is it faster to add something to the head of the list or the tail of the list? Yes. Correct answer, Jesus and Ron. So it's if it's a data structure like this, it's much faster to add something to the head of the data structure than to the tail, because to get to the tail, you have to go, okay, you go right, I go right, I go right, I go right, I go right, and boom, I put something here. Versus if you're adding something to the head, you just boom, I'm at the head, I put something there. Right. Um, because of this underlying data, we can add something to the head of a list in a very simple way using cell notation. So let's look at this piece of code right here. Drop it in the chat. So let me clear this. There you go. All right. So what's going on here? So here we're saying, I'm saying my list. I'm pinning a face, right? This tips fast, but I'm saying my list is of type list of PatUD, and the data is 2, 3, 4, 6. So we're giving my list that, and then we're saying, Cohort, make a cell of the number 1 and my list, and then we're casting that result back to a list of PatUD again. You press enter, boom, we got the list 1, 2, 3, 4. So what we just did with the underlying data looks like this. So this underlying data that we started off with, my list, was a binary tree like this, 2, 3, 4, sig. And it's just so easy to add something to the head of the list. We just take this whole thing, put it here, and then put this 1 as a left branch. That's exactly what we did with this Cohort. We said 1 is a head, my list is a tail. And you could have done the same thing with the sugar syntax for Cohort. So it's just a bit even more simple. This is the same. We're declaring my list. And here's a difference. We're just literally making the cell of the number 1 in my list. And then we're casting it back to a list. And boom, same thing. This casting is important because if you don't do this, the Hoon compiler will actually interpret this. So here what I'm doing, I declare my list again, and then I'm making a cell of 1 in my list. 1 is the head, my list is the tail. But I'm not doing any casting. And I'm gonna get this weird thing. So the Hoon compiler is saying, okay, you made a cell which has 1 as a head and a list as a tail. So it doesn't automatically assume this whole thing is a list, even though it has the correct structure. To make the compiler believe that it's a list, you do have to do this casting right here. All right. Any questions on that? Appending something to the head of a list using cell notation. All right. No. So with the sugar notation, it succeeds if you keep this casting in. So here we're declaring my list to be 2, 3, 4. We are using the sugar notation here. So we're saying let's make a cell of 1 as a head, my list as a tail. But we have this cat in front, which says interpret this data structure as a type of list of PatUD. And it works. If you do the same thing without the ket-hep, it also works. It doesn't fail, but it just is not interpreting this as a list. This and this are the same knock data structure, but here the compiler is saying, this looks like a list to me, it's a list. Whereas the compiler is saying, this looks like a cell with one as a head and a list as a tail. So yeah, same data structure, just different interpretation. It's not believing the whole thing is a list unless you make that clear. All right. Any other questions? Okay, so as I mentioned, an empty list or the null list is just a single character sig. So I can cast this character to a list of anything. However, Hoon has a special type for a list that you know are not empty, which is called lest. So it's a bit funny, but lest is a type of non-empty list. So you use it just like you used the term list. But like I can cast this 1, 2, 3, 4, 5 sig to a list. I can cast just sig to a list, but I can cast the first one to a list that also works, but I cannot cast just sig to a list. That is going to give you a failure because list is just like list, except it excludes this one case. And there's a reason that this type exists. If you know your list is non-empty, if you know it's a list, the compiler will attach faces to the head and tail of the list, which make it easier to navigate the list. So, for example, if I'm saying this 1, 2, 3, 4, 5 sig is a list of pat-UDs, I'm giving it the face A. Then I'm saying, let me get I of A. Is there an I of A? Yes, it is. It's the head of this. It's just the number 1. Put that in the chat for you guys. And you can also grab the tail of it with T.A. So if you recall how lists are structured like this, whenever you grab the tail of this rightwards branching null terminated tuple, whenever you grab this tail, it's also valid. So that means if I grab the tail of A, which has this structure, that's also going to be a list, which is 2, 3, 4, 5. Right. And if the compiler doesn't know that it's it's non-empty, you will get a find.fork error. So that's saying you're trying to call it with this face, but it doesn't exist. There's another way that you can make the compiler know that a list is non-null. So let's look at this piece of code right here. So here we're saying, let me assign 1, 2, 3, 4, 5 to a list of pat-UDs. Let me cast to that, and let me assign it the face A. Then we're saying, what's sig? This is kind of the new thing, right? We learned this last lesson. What does this rune do? Let's review that. What sig takes 3 children, says if this is a sig, do this. Otherwise, do this. That's it. So it's branching on whether this is sig or not. So this code, I'm at this code. Oh, and we have this new rune zap zap. We haven't seen this before, but zap zap just crashes. Like, it's very simple. If you do a zap zap, press enter, you get a Hoon expression failed. So it just means crash. So interpreting this line of code, this says, if A is sig, then crash. That means this is the last branch of this what sig. And if the code is in this branch, the compiler knows that A is not sig. So then if you're here, it knows that A is non-empty. So it's going to cast this to it's going to upgrade this to a list instead of a list. And it's going to let you grab that I and T of the list. So let's try this code. Boom. I grabbed I.A. That's the head of the structure, and it's the number 1, and it worked. I can do T.A, and it's going to give me 2, 3, 4, 5. All right. T is for tail. I is for... Good question. I'm not sure why these particular letters were chosen, but good question. All right. So yeah. So any questions on making the compiler know that a list is non-empty and then grabbing these I and T faces? Initial. Yeah, there you go. Good. I accept that interpretation. Is list to list casting a common practice? Yes, though I feel like I see this what sig more often. I see this more often because then you get like you have a bit more control over your crashing versus crashing based on like if you cast something empty to a list, you also crash, but you get a like a you get a midnight like this is like a compile time crash, and this is I mean zap zap is yeah. I see this one more often. You can use both of them though, but this is definitely common because it's very common and very useful to use these I and T faces to grab when you're working with lists to just to grab the head and grab the tail. Um, One of the reasons you want to do this is because like if you unknowingly have an empty list and you could think like, oh, I can just grab the head and tail bit with lark notation, right? Like I can say, let A be a list of like 1, 2, 6. And I can be like, okay, I can just use lark notation, right? Like grab the head of A, boom. Um, T dot A, or sorry, lark, there. But if you like if you have a variable, like you don't know what this is gonna be, and if this is like the empty list and then you use lark, yeah, you also get a crash there. So it's a bit more type safe to like it's a bit more safe to make sure this is the case and then use those faces. Um, okay, so if there's no more questions on that, we'll be moving on. All right. So Hoon comes with a very comprehensive library of gates to manipulate and use lists. And because of this, lists are a great way to represent data because there's just so many standard utilities that you can use to use them. So here's a link that we can use. Oh, this is old. All right. We're going to find the list utilities page. List logic. There we go. All right. So here's the link. And all this stuff right here are different things you can use to work with lists. So very comprehensive, very useful. Let's go through some examples of these. All right. So one bit of inconsistency in these is some of these will take a null terminated tuple that's not cast to a list, and then the internal logic of it cast it to a list. And others of them will fail if you haven't cast it to a list. So they just some of them behave a little different on that. But if you always cast your input to a list, you won't have a problem. So let's go through a simple one. Flop. Just reverse the list. Very simple. Flop 1, 2, 3, 4, 5, 5, 4, 3, 2, 1. Gulf. Gulf takes 2 atoms and is going to return you a list of that range of atoms. So Gulf 520 is going to give you 5, 6, 7, 8, all the way through 20. Lent returns the length of a list. This one also doesn't require a typecast. So length 1, 2, 3, 4, 5. And because it doesn't require that typecast, you can also call it on just sig. Snag. Snag takes an index and a list. Hermes says, are these dojo specific? No, these are general Hoon utilities. That's a good question. So you can use these anywhere in your Hoon code. The snag takes an index and a list and gets the thing in the list at that index. So snag does need to know that your input is a list. So we're going to cast it. We're going to cast that structure. We're going to cast this tomato, cucumber, orange, avocado. Snag 2. What's the thing in the 2 position? Pretty sure it's cucumber. Oh no, right, because it's indexed by 0. So this is the 0th position, first position, second position. So if we did snag 0, gives us tomato. So snap replaces the element at a position with another element. So I'll put this code here for you guys. Here we're saying snap is going to take a list, an index, and a thing to change. So let's change orange into pepper. And there we go. Tomato, cucumber, pepper, avocado. The reason this formatting looks like this is because a list of pat-t is actually a special type called a Wayne, and the dojo recognizes a Wayne and gives it a different formatting. You don't have to worry about this too much for now, but this is correct. is a correct output of this. We can sort a list. So sort takes a list and a comparison gate as arguments. A comparison gate is just any gate which takes two nouns and returns a send.y or a send.n. Then it uses that comparison to sort the list. So to understand this, let's see an example. So here we're saying sort this null terminated tuple. I didn't cast it, but you don't have to for sort. Let's sort 5379 with LTH. So if you recall what LTH is, that's a gate which takes two atoms and returns yes if A is less than B and no otherwise. So we're going to sort these with LTH. And what's that going to do? It's going to sort them from smallest to largest. And we can replace that LTH with GTH. And then that's going to sort them from largest to smallest. Pretty neat, right? Weld, we can stick two lists together. Weld concatenates two lists, so it also doesn't require casting. But here we're saying weld 1, 2, 2, 3, 4, 5, and we get 1, 2, 3, 4, 5. This one roll. Roll does something very interesting. So I'm gonna give you an example, and maybe from the examples you can infer, you can tell me what roll is doing. Okay, so I'm going to give you three examples here. So roll, we don't teach this limo anymore. It's just list UD. So roll, roll does need you to cast this. So we're going to roll this list of 1, 1, 1, 1 with add. It's going to give you 4. If we roll 1, 1, 1, 1 with mole, it's going to give you 1. And if we roll 1, 2, 3, 4 with mole, it's going to give you 24. So yes. So does anyone else see what's going on here? Ron is very on the ball today. Yeah. So this is the equivalent of reduce in other languages. That's correct. So in particular, what it's doing is we're saying, let me apply add to all of these in order, accumulating a result. So we're going to add 1, 1, get 2, add 2, 1, get a 3, add 3, 1, get a 4. Here we're saying, let me multiply 1 by 2, get a 2. Let me multiply 2 by 3, get a 6. Let me multiply 6 by 4, get a 24. So there's a bit more complexity in how this works, but we won't get there until we learn about gates, which is in an upcoming lesson. All right. So another very interesting utility, turn. So turn, so like how roll is the equivalent of reduce, turn is the equivalent of map in other languages. So here we're saying, let me turn 2, 3, 4, 5, 6 with the gate dec. And dec is a gate which takes an atom and just reduces it by 1. So we get 1, 2, 3, 4, 5. So turn is like map. It's just saying, let me take this gate and apply it to every element of this list. Yeah, good question, Hermes. So roll, I think that's why roll makes you understand this as a list. So if we did put a 0 here, if we put a 0 here, or if we did this, even if we did this, oh no, that's going to give you a type. But if we put a 0 here, that is going to give you 0. But it's not interpreting this final sig as a 0, because when you cast it to a list with this, you're saying, I interpret this as part of the structure of the list. I interpret this not as a number 0, but as the terminating character of a list. So we're not actually including this in the rule. Yep. Yep. Good question. All right. So back to turn. So we just turned this structure with decrement. But the gate that you use doesn't have to be a predefined one. You can write a custom gate and use it for any of these. You can use a custom gate for roll and turn and anything else that takes a list. So we'll learn how to write custom gates soon, but we're not there yet. Here I'm gonna give you one, and I'm just gonna say that here I'm assigning mul5 to a gate which takes a number and just multiplies it by 5. And here we're turning 1, 2, 3, 4, 5 with our mul5 gate that we just wrote. And we get 5, 10, 15, 20, 25. Pretty nice, right? Also, like, turn can do, like, it doesn't need to preserve types, which is kind of interesting. So in this example, I'm writing a gate num to ship. It just takes a PAT-UD number and gets you the PAT-P representation. So if we turn 1, 2, 3, 4, 5 with num to ship, we'll get all these PAT-Ps. All right. So one last one we'll take a look at is skim. So skim takes 2 arguments, a list and a gate. That gate takes 1 argument, which should be the type of the thing in the list, and returns either send.y or send.n. And skim is going to take that list and that gate and return the list, but without anything that gave you a send.n. So with only the things that made the gate say send.y. This is the equivalent of filter in other programming languages. So for a simple example, here's a simple example. Here we're saying, here again, I'm defining a custom gate. I'm just going to tell you this is even. It's just taking a number and just returning a send.y if it's even and a send.n if it's not even. Don't worry too much about what's going on in here yet. Then we're saying, let me skim this list of numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 with the is even gate. And then we're just going to get the list with the even numbers remaining 2, 4, 6, 8, 10. All right. So any questions on the list library or lists in general?
Yeah. Oh no. Well, how come sometimes how come sometimes it has like that list sugar syntax you showed us with just the little tilde in front, and
Yeah.
sometimes it has actual like named eye and tail? Is that
Yeah.
you cast to a list or?
Yeah. So that's a great question. So this, whenever it knows that your list is a list, when the compiler knows that your list is not empty, then it's going to automatically attach these faces to it. And these faces make your life easier, right? If you're working with this list. So that's why it looks like this, because the compiler said, I know it's not empty, so I'm going to upgrade this by attaching these int faces. And the reason it knows it's not empty is probably something to do with the internal workings of Skim. Probably something in Skim made the compiler know that its result was not empty, and it attached these. Does that make sense?
Yeah.
Good question. Ron says, does skim not work with an empty list? Well, that's a good question. Let's try it. So if we give it an empty list, we cast it. Oh, well, I have to define this. It does work with empty list. If we don't cast the empty list, then it also works. There's some inconsistency in how these are implemented. But yeah, seems like skim is happy if you don't cast. Let me see if this works in our original case. If I delete this, yeah, so it works. This is probably due to just the logic of how skim is implemented internally, which you can see here. Yeah, it might have to do with this, but basically, if you don't cast the empty list, it gives you the empty list back. However, if you don't cast the non-empty list, it actually is going to fail. So yeah, so it's generally good practice to cast things. That prevents the most errors, that passes information to the compiler. So yeah. All right. Any other questions? All right. So let's get into our second major topic of today, which is Hoon's Hoon's text system. So so far we've learned about and used the pat-t type, which stores basically any text as an atom, as a single value, and the pat-tas type, which is also an atom, but it's more restricted, right? Pat-tas is only lowercase ASCII letters, the HEP, and the numbers 0 through 9. And we've learned that it's both a value and it's also its own type. This graphic represents all the ways that text can be stored as atoms. In particular, there's one more that we haven't learned yet. Pat-ta is between pat-t and pat-tas. So it's more permissive than a pat-tas, but less permissive than a pat-t. It's called a not. It permits only ASCII letters, and it's used for certain system labels. So if you want to check whether a certain piece of text is valid as any of these, you can use the library gate sane. So sane is a gate that builds a gate. So here's how that works. So you call sane as a gate on the aura pat-ta. So here's a tall form, here's a shorter form. The result of this is a gate, which takes a text and tells you if it's going to work as a pat-ta. So here we're using this gate, calling this gate on this input. We're seeing if this text angstrom is valid. And let's run that code. No, it's not valid. So, and yeah, I think knots don't permit these characters. That's why this doesn't work. So, and you can use this with pat-t and pat-tas as well. So suppose that you'd like to send some Urbit data like pat-p from your backend, your Urbit backend to some web frontend. If you could like to convert a value like that to a chord, to a text, you can use the gate Scott. So Scott is a gate which is going to take any atom, like sample palnet. You tell it that that atom is a pat p. Here you use a sen p instead of pat p. But that's just telling it it's a pat p. And then you're going to convert it to a text. This is actually a not. This is this syntax means it's a not a pat TA. We can convert the result of that to pat p. If we add a casting to the front like this, then we'll get the same thing as a pat t. Here we're saying, let me take this hexadecimal number. I'm going to interpret it as a UX hexadecimal, convert it to a text, and then make sure we interpret that text as a pat t. And then we get this number as a text string. It's pretty useful, right? Now suppose you're going the other way around. So say a user is putting some text into your app and you want to store that as some value in the backend. So maybe not text, but some like Urbit data type, right? So you can convert text to atoms using slav. So if I do slav sen p sample palnet, so this is a chord, this is a piece of text, right? With these single quotes, we're saying, let me make this piece of text try to fit sen p. It's going to work, but it's actually going to return the raw atom. So you do need to cast that back to your desired type, and boom. So this piece of code, this call to slav with the casting, took this text and gave you back the pat p data type. So that's pretty useful, right? And here's just like the sugared version of that. Call slav on this, cast it to a pat p. If this text doesn't work, you get a failure. It just crash. So that's because df is not a valid part of a pat p. All right. So besides pat t, pat ta, and pat ts, which all represent text as atoms for single values, there's one more possible representation of text in Hoon. You can actually represent text as a list, which is powerful because it gives you access to all the list library gates that we learned while working with a piece of text. So in particular, this is what we call a tape. A tape is a list pat td, like this, list pat td. This pat td means it's a data of type pat p, but this d means it's limited to 8 bits. So a tape is a list of pat t data, but each piece of data is no more than an 8-bit chunk. So here we have the data representation of a list of a tape of text stored as a list pat td. So this data is saying the text I space am space the, and so on and so forth. These numbers represent the addresses that you're storing each of these pieces of data in the binary tree structure. And yeah, so it's stored in a list, right? We've seen this structure before. When you're representing tape data, it's using double quotes instead of single quotes. That distinguishes it from a chord, which uses the single quotes. But a tape can represent exactly the same data that a chord can. So these are all valid tapes. So to cast a piece of data to a tape, these are 4 equivalent representations. So here we're calling the gate list, the mold maker gate list, with input pattd. This makes a mold, which is a list of pattd, and we're casting this welcome to Mars with that, right? Here we're just sugaring the senhep. This is a little neater. We're saying cast this to a list of pattd, right? Now the little bit curious thing here is the term tape is exactly equivalent to this in Hoon. So these are exactly equivalent. We're just replacing list pattd with tape. And we can either even sugar this cathep. So this is the shortest version. We're casting welcome to Mars to tape. So I mentioned that you can represent anything that a chord can, also as a tape, and you can convert between them with these gates called crip and trip. So you can remember them as crip is chord rip. You're ripping a tape to a chord. And trip is tape rip. You're ripping a chord to single quotes to a tape. Now you got the double quotes there. Tapes are easier to work with than chords for the aforementioned reasons, but they use about 6 times as much storage as chords do because they're stored in this list structure. So a common practice in Hoon is to use chords for data storage, convert to a tape for processing the text, and then convert it back to a chord when you're storing it. Why the uppercase D in pattd? That's a good question. I wonder if it would also work if it's a lowercase d, but everything I've seen, the convention is a pat is a uppercase. Let me try list pat t lowercase d. Oh, so that's actually different. Yeah, so actually a lowercase d is actually a different meaning than an uppercase d. And I think it indicates something about the data type. So this is actually an important note. If you use a lowercase d here, it's gonna give you something different. And I don't know entirely why that's the case, but I do know that this uppercase D denotes the 8 bits. All right. So, yep. So I'm just gonna be, we are at 11. I am gonna be a few more minutes, so I apologize for that. Should be about 3 or 4 minutes, honestly. So let's go through some tape utilities for working with tapes. You can convert an atom of any aura to a tape with scow. So scow says, let me take this atom, like this is a PAP-P. I'm telling it it's a PAP-P, and I want that data as a tape. Boom. Here's with a hexadecimal. You can make a tape all uppercase with the gate cuss. You call cuss on this text, you get uppercase text. And you can use cas to make any text as a tape, all lowercase. Trim takes an index and a tape and splits the tape into 2 tapes at that index. So Merry Christmas and Happy New Year. Let's trim it at 16 and we get a cell of Merry Christmas and Happy New Year. And those are tape specific, but we can use the list library functions that we just learned. So the gate find is actually a list library gate, but we can use it on a tape because tapes are lists. So find returns the index of a matching substring within a string, or a matching sublist within a list. And that's going to tell you that the substring needle is at index 12. You can use flop to reverse a list and to reverse a tape. You can use weld to concatenate two lists and concatenate two tapes. You can use snap to replace an element at an index, and you can use snap to replace a letter in a tape. So one thing you do need to be careful with is these individual letters are not pat T's, but they're pat TDs. So if you forget and you're like, oh, let me replace oh, that works. I think if you cast this to a pat T. Okay, but yeah, there's some inconsistencies, but basically these individual letters are pat TDs. It's safer to do this because I think you can give a letter that's like a rare letter that's not going to work, but the letter C is small enough. It fits within 8 bits. But yeah, here replacing the thing at letter 10. Yeah. Here's replacing the thing at letter 10, index 10, which is the letter B, with the letter C. And boom. And we can add something to the head of a tape with cell notation because we can add things to the head of lists with cell notation. So here we're adding A to B, C, D, E, F. We get A, B, C, D, E, F. You can actually render any Hoon expression as a tape with these angle brackets. So this is the floating point square root of the number 42. We put these angle brackets around it. We'll get that result and we'll get it as a tape. You can interpolate a tape within another tape. So here we're setting the face X to the text Saturday. And then we're evaluating good morning. It is bracket X bracket. And what's that going to do is it's going to grab this variable and interpolate it in them. And so if you change the value of that, if you change X to Sunday, you're going to get morning to Sunday. And you can combine both of those two things. So here we're saying let X be the floating point square root of 42. We're putting angle brackets around X to turn this Hoon into text, into tape. And then we're putting curly brackets around that to say, take that tape and put it in here. And boom, we get square root of 42 is as a piece of text. So this kind of stuff is super useful when you're working with apps and front ends and whatnot. All right, so thank you for your patience. That brings us to the end of the lesson today. Are there any more questions today? And at this point, you are free to go if you'd like. So Ron says, is there sugar for casting a pat TD back to a pat T? See ya. Nice having you. See you folks. All right. All right, yeah, let me stop the recording at this point.